Assalamualaikum and hi everyone. So today I would like to share about Kepler's law of planetary motion. So the Kepler's law of planetary motion actually it describes the motion of the planets around the sun, and it also reveals the fundamental principles governing their orbits. And this law also apply to the motion of the moon orbiting the Earth and satellites orbiting the Earth. So this law derived by Johannes Kepler in the early 17th century, and it's relate to the shape of the planetary orbits, okay, relates to the variation in orbital speeds, and also it's relate to the relationship between a planet distance from the sun and its orbital period. Okay, so first, we look at the first Kepler's law of planetary motion, also known as the law of ellipses. Okay, so this first law states that the orbit of a planet around the sun is ellipse with the sun at one of the two foci. Okay, so this law basically it describes the shape of the planetary orbit. Okay, and the planetary orbit is not a perfect circular; it's an ellipse orbit, and when ellipse orbit it has a few features, okay, so which is in ellipse we have two foci, okay, the two foci, so meaning that it has two focal point, okay, two focal point, which is for ellipse focal point is away from the center, let's say the center, so basically in ellipse is the center, so basically in ellipse it will move away from the center, so it has two focal point, and the sun just located at one of the from the two foci, okay, and in ellipse it has a major axis, semi-major axis, and semi-minor axis. Okay, so look at this elliptical orbit. So this sun is located here, okay, so the sun is located here, okay, so this is the center of the ellipse orbit, okay, and this is the focal point, okay, one and second focal point here, okay, and sun just located one at one of focal point, okay, like say this is the planet orbiting the sun, okay, so in ellipse we have a few features, which is the center to the edge is we call semi-major axis, this one, so this one is a semi-minor axis, okay, and uh, the for the object located far from the uh, object at the center, not at the center, at the focal point, okay, so this distance we call periapsis, okay, and if object located near, okay, to this mass, so this distance we call apoapsis, okay, so the shape, okay, the shape of the ellipse is depend on the eccentricity value, okay, so we will discuss further on the other topics, details about elliptical orbit. So next we move to the uh, what is the implication of the first Kepler's law. So the distance between a planet and sun change, okay, as the planet move, okay, so meaning that if planet moving from the sun, so every time it's moving it's not has the same distance, so the distance keep changing when it's moved around the sun, okay, and then this first Kepler's law challenged the long-held belief that planets move in a perfect circles. Okay, so next we move to the second Kepler's law, also known as the law of equal areas. For this second Kepler's law, it states that a line joining a planet and the sun sweeps out equal areas in equal time. Okay, meaning that if this planet here moving to here, Okay, so then it takes 6 months. Okay, so this is the swept out areas. So this swept out areas is equal to this swept out areas, which is when the planet move from here to here is also take 6 months. Okay, so this is the second Kepler's law. Okay, so which is in mathematically we describe as dA over dt is constant. Okay, so dA over dt is constant. The change of surface over change of time is constant. Swept out area, A is swept out area. Okay, and the key feature of this law, okay, is mentioned that orbital speed variation, okay, area swept out, and also it's related to the conservation of angular momentum. For orbital speed variation, actually is referred to the planet. When the planet move, okay, near to the sun, the orbital speed is increasing, and when it moves away from the sun, it start to decreasing. Okay, and for area sweeps out, okay, so when you make a line, okay, from the sun to the planet, so let's say this is the planet here. Okay, so it takes 1 month to move here. Okay, so 1 month, so the areas, and then it takes another month here. Let's say 1 month, so the area sweeps, okay, the area swept is equal, okay, it's constant. Okay, so this is what they mean by area swept out. Okay, and the conservation of angular momentum means that the planet move, when it planet move near the sun, okay, this orbital speed is increasing due to the planet to maintain its angular momentum. Okay, so to maintain this angular momentum, this orbital speed is increasing. So when it's moved away from the sun, the orbitals start to decreasing. Okay, so this is the key feature of the second. So this law, okay, is explain, okay, why the planets not move at constant speed, okay, along its orbiting the sun. Okay, and when it reach the perihelion, okay, when it reach the perihelion, okay, the speed is minimum. Okay, and at aphelion, when it's perihelion, okay, when it's perihelion here, the planet speed is the maximum. Oh, so at perihelion here, okay, so at perihelion, okay, at perihelion, so I did something, I made some mistake just now. Okay, so at perihelion here, a planet has the maximum speed here because it's close to the sun. And at the perihelion here, okay, which is far from the sun, the farthest distance from the sun, the planet speed is at the minimum. And but okay, the total kinetic energy remain constant wherever the planet located in the orbital uh in the orbit. Okay, in the orbit. Okay, so but when it close, it has higher kinetic energy but lower potential energy. When it far, it has a lower kinetic energy but higher potential energy. And then next, we move to the third Kepler's law of planetary motion, which is also known the law of harmonics. Okay, because why? Because this law states that the square of the orbital period of planet is proportional to the cube of the semi-major axis of its orbits. So meaning that, okay, the orbital period, okay, the T, or the orbital period of one planet, time taken for one planet to complete one revolution, okay, the square of orbital period is proportional to the cube of the semi-major, okay, the distance of between center to the here. Okay, this is semi-major. Okay, that this is very harmonious relationship. Okay, so this is the third Kepler's law, straightforward. Okay, and for this law, okay, we can understand that the planet, when it far from the sun, it will have the longer orbital period. Okay, and the four object orbiting the same central body, the ratio t square over a square is constant, meaning that the t square over a t square, okay, over a to the power of 3 equals to constant. If, okay, if the object orbiting the same central body, meaning that if the sun, okay, so Mercury period over semi-major, uh, semi-major is equal to the Earth and other planet. Okay, so this is the key feature of this law. Okay, so the implication of this law, okay, so we can calculate the orbital period of any planet or object if its semi-major is not. If we know the semi-major, and we can calculate the orbital period. Okay, it not just apply to the planet, but this law is also applied to the moon. Okay, if we want to calculate the moon's orbital period, we just know its semi-major. Okay, and also it's applied to the satellites or artificial object orbiting a central body. Okay, and so by comparing the periods and distance of the planets, so the astronomer can scale the solar system relative to Earth orbit. So this is the impact of the third Newton's law. So that's all about uh, Kep Kepler's law. So the details will be explained in the next session. Okay, that's all. Thank you.